All right, hello everyone. Welcome to another Unit 2 video. This one is going to be a triple your pleasure video because we're going to cover three lessons in one video. Lessons 5, 6, and 7, all of which have to do with the same concept of the relationship between factors and zeros. Now, the reason why we're going to do this as almost three lessons in one is because we've very recently handled working with this very thing with quadratics. And you might recall something called the zero product property. The zero product property. That, sure enough, is going to work for polynomials in much the same way that it worked for quadratics. And so this is one of the things that I had said last video, that some properties of quadratics can be generalized to all polynomials, x to the third, x to the fourth, and so on and so forth. This is one of those things. Okay, so some of the things that we're going to learn about here. I can identify zeros of polynomial functions written in factored form. Um, we did that with quadratics already, so I think we could handle that one pretty quickly. And a lot of this, just reading through some of the other bullet points here, you're really looking at, again, the idea of the equivalent form between standard form and factored form. The good news, though, with this is polynomials in general don't have a vertex form. So we don't have to worry about that. Um, and then we had a quadratic formula. There's really no good cubic formula to solve x to the third. So, we're not going to learn any fancy crazy formulas or anything. Like, there is a process to solve them, but we're not going to cover that here. Um, so we are going to look at the things, though, that we can easily bring over from quadratics, and standard form and factored form are definitely one of them. Last time in class, we looked at the relationship of the y-intercept, so we're going to bring that right into play here. Okay, so warm up. What values of x make these equations true? Okay, so remember, the zero product property states that if a times b, if a times b equals 0, then a equals 0 or b equals 0, or both. Um, Although for the purposes of these expressions, you can't have multiples of these be 0 all at the same time. Um, but what's interesting to note is this is the generalization of two factors. But what if I had three factors? Is the same thing true? If a, b, c equals 0, then a equals 0, or b equals 0, or c equals 0? Do you think that's true? Certainly is, because let's say, for instance, we know these products are 0, and let's say we know that b and c are not 0. Well, you can multiply them together and maybe you get like 45. But then as soon as a is 0, um, as soon as you multiply by 0, the entire expression automatically becomes 0. So it doesn't matter whether you have A, B, C, D, E, F, Christmas tree, however many factors you have, this is always going to be true. So we're going to use the same rule that we did during our last unit, right? So what values of x make these equations true? So if x plus 4 times x plus 2 times x minus 1 equals 0, one of these factors has to be 0. So either x equals negative 4, because then that would be 0, or x equals negative 2, or x equals positive 1. And the same thing with this one, you're going to have a negative 4, or negative 2, or x equals 1, or x equals 3. So again, for each factor, what value of x makes it equal to 0? Now, one thing that we hadn't dealt with a lot last time with quadratics is when you have factors that are squared and you have multiple factors, right? So here's an example. Um, what values make number 3 true? Well, in this particular case, again, you might think, well, negative 4, right? And think about it. Negative 4 plus 4 is 0. And what's 0 squared? Well, that's just 0. And x equals negative 2, just like before. Yeah, no big deal there. Except this one only has 2 solutions. Um, Despite the fact that it actually has 4 factors. If I were to write this out, I would have x plus 4 times x plus 4 times x plus 2 times x plus 2 equals 0. Because, squaring means I can multiply it by itself. Um, but because of the repeat of the 4s, I don't have to say x equals negative 4 or x equals negative 4. I don't have to say that because just having one negative 4 is good enough to make this expression equal to 0. So when you have a factor that's squared, it doesn't change the x-intercept. Now, it does change the behavior of what the function does at that point, but that's a story for another time. For the rest of these, they're going to act exactly as we would before. So the negative 2 in front of the factor does not affect x-intercepts, right? Because if x is 4, for this factor, 4, if x is 4, right, then you get 0. 0 times negative 2 is still 0. And if this number is something different, let's say 5, and you get a 1, you multiply it by negative 2, you get something that's not 0. So if one of these factors is 0, you're still going to multiply by negative 2, and it's still going to be 0. So x equals negative 4, or 2, or negative 1, or negative 3. So again, the zero product property is king here, okay? And again, only works as long as the expression is equal to 0. Keep in mind with fractions, if you recall, expressions like this one here, you can divide by the front number. So it's the value of x here, it's x equals negative 8 divided by 2. Now that happens to be 4, and certainly negative 4 works here. So x equals negative 4. Same thing here, x equals positive 3 divided by 7. 3 sevenths times 7 is 3, and 3 minus 3 is 0. X equals 10. So this simplifies to negative 4. So my solutions here are x equals negative 4, x equals 10, and x equals 3 sevenths. And there should be an order between each one of those, because only one of those is going to be true at any given time. Okay. Same thing with these. Just again, make sure that you put it in factored form. So x squared plus 3x minus 4. You factor it. That becomes x plus 4 times x minus 1 equals 0. And you get x equals negative 4 and x equals 1. Okay, so same thing. And again, you can check that. You'll find that that totally works. So again, no differences there. With number 8, again, be careful. You have an x squared minus 4. You can factor that. And so you have x plus 2 times x minus 2 times x plus 9 equals 0. Remember problems like that? There was a quiz that had a question like that on there. So x equals plus or minus 2, or x equals negative 9. Now, you could say x equals 2, or negative 2, or negative 9. I took a bit of a shortcut there and just said x equals plus or minus 2. You can do that. If you have two factors that are the same number but opposite sign, that's totally fine to do, in my book at least. If you have a different teacher than Mr. M, then maybe not. I don't know. Okay. All right. So as you see, the zero product property works just the same way with whatever kind of polynomial that you have to deal with, right? Okay. So graphing them is going to be exactly the same, right? So those solutions, when we dealt with it with parabolas, they became x-intercepts. Same thing's going to happen here, right? And so if I look at, okay, we got 1, 2, 3, we've got A, B, C. Can we match them up? Okay, so if I have the first one, well, let's see, x equals 5. So again, what are my solutions here? So my solutions are x equals 5, x equals -4, or x equals -3 halves. Okay, does one of these graphs match that? Okay, um, 5, -4, 3 halves. It's not A. No, oh, look, it's C. So this must be C. Okay. And because, again, those solutions certainly match there. No picture of the graph needed. For number 2, y equals x minus 5. So it's got a solution at 5. So right away, it looks like we have a solution at 5. That looks like that's probably going to be A. But let's check the other ones. It also has a solution at 4. And it also has a solution at -3 halves. So, yep, that matches, that matches, that's A. And just matching here, again, make sure that even though it's the last option, make sure there's no funny business. -5, the x-intercept will be at -5, the x-intercept will be at 4, and the x-intercept will be at +3 over 2, 1.5, there you go. Okay, perfect, so it looks like that's certainly B. Gab, there we go. All right, isn't it nice when things just work? Okay. Oh, Return of the Box. Ooh, I was looking forward to the sequel. Sequels are never as good as the original, though. Unless you're The Godfather. Fun fact, as of the year 2022, The Godfather Part 2, the only sequel of a movie to win Best Picture, Oscar, 1974. Both Godfather and Godfather Part 2 won Oscars in their respective years. Okay, Return of the Box. Now, this time, no folding necessary. We've already done the work needed for the function. Okay. Um, but one of the things that we looked at was that the concept of the open top box can be generalized, right? So remember that the box was created by cutting squares out of sides of pieces of paper, and that leaves these 4 flaps that can be folded up to form the side of the box. Now, these 4 side lengths are x, right? X, 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 X. That's a lot of x's. And then let's say we have a piece of paper that's 8.5 by 14. Okay. So the volume is given by this function here. And again, do you see why this has to be the volume function? Um, the long side is going to be 14 units long, right? And in order for this part to fold up, for this bottom flap to fold up and form a side, it's going to be chopped off by these 2 x's. So it's going to be 14 minus 2x. Likewise, the width is 8.5, but you're going to lose 2 x's before you fold it up. And then when they fold up, it's going to stand up by the actual value of x itself. Okay. All right, so identify the degree leading term of the polynomial. Oh, how do we do that? What's degree? Degree is highest exponent. Okay, so value of the highest exponent. All right. So what, 1? Is this a first degree function? Because none of the x's have an exponent on it. But if that's the case, then what's the leading term? Oh, that's yucky. How do we figure that out? Remember, degree of polynomial only comes about when it's in standard form. So in order to do that, we're going to have to distribute this out. Okay, so how do we distribute this out? Because it looks like we've got three things, right? Okay, how do you distribute with three objects? Easy. You pick two of them, you multiply, and then you multiply the third. So let's start with the first two, right? So we're going to multiply 14 by 8.5. Side calculator, hello. Let me wake my phone up here. Side calculator, 14 times 8.5, 119. Okay, so we have 119. Let's see, minus 28x. 8.5 times 2 is 17, so minus 17x, and plus 4x squared. Now we're going to combine our like terms. And so 28 and 17 combine to give you 45. And so what you're going to have is you're going to have 4x squared minus 45x plus 119. Oh, but now we have this extra x, right? So what happens when you multiply by x? You're going to multiply this expression by x, so all the powers are just going to go up by 1. So now you have 119x, 45x squared, and this is now, let me use my fancy eraser here. Come on. Oops. Oh dear. We have now 4x to the third minus 45x squared plus 119x. That is going to be the volume of that box given the value of x. Okay, so what's going to happen now? Let's look at some of the properties of this, right? Degree is going to be 3, and what makes this nice is because we're dealing with volume. Volume is always 3 dimensions, a length, a width, and a depth. X covers each of those. That's why it's a degree 3. So it's a degree 3. And the leading coefficient is 4. The leading coefficient is a 4. Now, it may not have been immediately evident in this original problem, but negative 2 times negative 2 is positive 4, and certainly the leading coefficient is 4. So that 4x to the third term, that's going to be what has the biggest effect on the characteristics of this function. But there are a few other things that are important as well. So next question. What are the horizontal and vertical asymptotes? Wow, intercepts. I'm getting pre-calc here. My goodness. I am not redoing a video just for that. Okay, so the biggest thing here is, well, let's start with the easy one. What is the y-intercept of this function? The y-intercept is the same as the constant term. The constant term is 0. So the y-intercept is 0. When the y-intercept is 0, it's also true that the x-intercept is also 0 because 0, 0 is the same point. So, and that comes from this factor here. This factor is just x. When we multiply by x, it's making all of these terms pick up an x, and the constant term of 119 is disappearing. When that does, it causes 0 to become one of the solutions. Okay, what else is an x-intercept? Okay, so from this first factor, it looks like 7 is a possible one as well. 14 minus 14 is 0. And what about this one? It's going to be negative 8.5 divided by -2, that's going to be 4.25 is the other x-intercept. Because 2 times 4.25 is 8.5, and then subtract from 8.5 and get 0. Okay, so we already know quite a bit about this function. Its x-intercepts, its y-intercept, and that gives us a nice, pretty clear picture. Now, going back to this question a little bit here, one question that often gets asked is what is a safe domain or a reasonable domain to use for x for this box? Um, a reasonable domain is going to be any value of x where all of these sides are all positive, because you want the box to have positive sides. And the only numbers of x that are going to make that happen are between 0 and 4.25. Once you pass the first x-intercept, um, then this middle term here starts to turn negative because x gets too big. So domain of the box would be 0x 4.25. Okay. Then that's just kind of a food for thought because that comes up in the homework a few times. All right. Let's look at this function here. Same thing, right? Except for the 1/2. So f and g are almost the same. They have the same factors. It's got the 1/2. Okay. So if we were to use some graphing technology, let's graph these functions and let's see how they're different, right? So let's take a look. So I'm just going to hop over to Desmos and let's write it out. We have x minus 2, oops, times, what's it again? It is x plus 3, x minus 7. And so we have that function. Oh, look at that. And it crosses, right where we thought it would. 2, -3, 7. If I scroll it out a bit, see it goes up, up, and then down, and then up again. Very narrowish, like, right? Now I'm going to use the same thing, but this time I'm going to put a 1/2 in front of it. 1/2 x minus 2, x plus 3, x minus 7. How are they similar? Same kind of curve, same general shape. If I look at this one, but clearly the 1/2 acts as sort of a stretch, right? And so the 1/2 takes the function and kind of compresses it a little bit into a bit more of a nice little compressed arch. And if I were to take this and I were to change this, one thing that you can do that I love doing this on Desmos, I'm going to change that to an A, and I've got a little slider, and you can change A, and you can see what the effect of A is. Step 0 plan, so let's do A from, say, -2 to 2. Okay. Oh, look at that. Oh, and when you turn negative, hey, the graph flips around. That's interesting. Because it goes negative. That's interesting. When it goes 0, the graph goes away. Because now it's a line of 0. So the graph flattens out. But then oh, that's interesting, isn't it? Okay. So that kind of describes a lot of what's happening with that scale factor, right? So the scale factor there, that is what influences kind of the stretchiness of the graph and some of the values that you see. Okay, so both polynomials are going to have degree 3, right? And that's pretty clear because when you distribute it out, you're going to end up with an x to the third term on both sides. So um, remember to rewrite this in standard form, you just pick two, you multiply them, and then get that result, and then multiply it by the third. Um, so you can do that by doing, say, like, if I do x minus 2 times x plus 3, right? Okay, so that's going to be x squared minus 2x plus 3x. So that's 1x minus 6. I'll leave the 1 there just for clarity. And then I'm going to take that and I'm going to multiply that by x minus 7. And so what I'm going to end up with is x to the third. Now, this is where it gets wacky because you kind of have to do x squared times minus 7. So I get negative 7x squared, and then plus an x squared term, x times x. So I get minus 6x squared, right? Yeah. And then I get 7x. So minus 7x minus 6x minus 13x plus 42. Okay, that's a bit of a mouthful. And you can check that yourself. I kind of did that quickly in my head. Um, if you have the 1/2 in front of it, you get the same thing, but you get a 1/2 of all of these numbers. So you would get 1/2 x to the third minus 3x squared minus 6.5x plus 21. Um, let h of x equal 3x minus 6, x plus 3, x minus 7. What do you think that graph is going to look like? Okay, different function, right? But here's the thing. Look at this x minus 2 term, right? The x plus 3's match. The x minus 7's match. This one also has an intercept of 2 because 2 makes this equal to 0. 3 times 2 minus 6 is 0. Same thing as this. Might it look pretty similar? Just maybe with a factor of 3? Let's take a look. So we'll close that. And let's say we have 3x minus 6, x plus 3, x minus 7. There you go. You get exactly what we had before. And so if I take that function and extend it out, and if I take this, and it's not going to go all the way up, certainly. Pretty close. Oh, wait. It kind of does. So right here you can tell, so 2.8, 2.93. Okay, so if A is 3, the two graphs are exactly identical. And so if I factor out the 3 and I get 3 times x minus 2, then yeah, I get exactly the same graph. So graphs with the same x-intercepts will tend to behave very, very similar to one another. Okay, so one thing that we can take a look at here, the constant term. Do we have to multiply the whole thing out to get the constant term? Well, let's take a look, right? If we go back to the previous slide, we multiplied everything out and we got a 42 at the end. But where does that 42 come from? It comes from negative 2 times 3 times negative 7. So negative 6 times negative 7, positive 42. So Negative 2 times negative 7. Yeah, that's 14 times 3 is 42. So regardless of how it looks, you get a constant term of 42. Same thing over here. You multiply by the 1/2, you're going to get a constant term of 21 because you get the same 42, but you have to multiply by a half. So that looks like that's what's happening here. So the constant term, 21. Whoops. Whoa. Hello. Marker's not acting right there. So constant term is 21 and comes from multiplying um, 1/2 times negative 2 times 3 times negative 7. Okay. All right, next little thing here. So we have a graph of a function. The function is x plus 1 times x minus 2 times x plus 15. We look at a window, we see this graph. Oh, that's interesting. It's quadratic. Not quite. How do we know it's not a quadratic? Well, other than it has three x's, right? So look at the x-intercepts. X equals negative 1, x equals 2. We see those points here. We see that point here. But then x equals negative 15. Oh, not on my graph. Let's take a look. Oops. So we're going to scroll a bit and just kind of show you where we did before. Cancel, 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 cancel. And so we have, what is it? What was it again? X minus 2. X plus 1. X plus 15. Okay, and at first, yeah, it definitely looks like a parabola, right? Because it's going all the way down. But oh, look at that. There's another line way over here. Okay, so the line does come down through 15 again. We just didn't spot it before because of how the axis is scaled. So it turns out there is a local min at negative 35 that we pointed out here, right? It looks like that's the vertex of the graph, except that's a local min, and we're only looking at that section of the graph. And if we go all the way up again, the graph goes all the way up, and it looks like it's going up forever, but it turns out there is, in fact, at 540.141, there is a local max before it comes back down again. So here's a wacky one. In order to see that this graph comes back down again and crosses at negative 15, that top point has to go all the way to over 540. Wow, that's wild. But that's technology for you. And so, because we expect there to be three x-intercepts, all we had to do was just zoom the graph out a little bit to show it. And there you go. And here is our graph. Goes up, down, up again. The larger factors that you use in here, the more pronounced and steep that this function gets. Okay. And so, a lot of this is just about choosing the appropriate viewing window. Okay. So what viewing window would you choose for the following graph? X plus 1, x minus 1, x minus 2, x minus 28. Whoa, okay. So, wow. In order to select an appropriate viewing window, one of the things that has to happen is we're going to have to figure out how far up and down the graph goes. And some of that is a bit Desmos, right? Okay, so let's look at this graph. So let's graph them in Desmos. 1, -1, -2, -28. So, okay, there we go, like that. Am I right there? X minus 2? Yep, perfect. So if we scroll in the normal section of the graph, you're going to notice that it does cross the x-axis. At first, again, it appears like it's 3 times, right? But we know better by that by now. It's going to also cross the 28. So we zoom the graph out a little bit, and sure enough, there's 28. And the graph is passing through 28. But look, that line is almost vertical. So we're going to have to pull the graph way out to show that, right? And so the question is, I guess now, do we have to go up the graph or down the graph? So this has got 4 parts to it. So the graph is going to go down and then up, and then you can see how it turns here. So it must be going back down this side, which means it's going to have to come up this side, which means we're going to have to scroll down, but not just down, 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 way down. Let's look for the let's look for the y-intercept here. Not y-intercept, I mean the local minimum. We're at negative 2100. Oh my goodness. Oh my goodness. We're going to scroll this all the way down. 9,000, 10,000, 11,000. What in the world? 20,000, 24,000. Uh-oh. I did something bad. Oh, oh boy. I just took my tech in my fervor to do this. I seem to have, um, how did I do that? I took my taskbar and I dragged it and made it on the right side of my screen. How in the world did I do that? Okay, hang on. I'm going to fix this because I do not like this one bit. Okay, guys, I'm back. I fixed that. I don't know what I did there. So we're scrolling this. We're at negative 21,500. We're looking for the local min of this function. And oh my goodness, what is going on? Oh, there it is. Wow. Hold on. Let's look, let's look, let's look, let's look. Scroll, 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 scroll. Wow. 58,000. Okay. All right. So that's a heck of a viewing window. Um, Wowzers. Wouldn't have pictured that one. Okay. So how do we select an appropriate viewing window for that? Um, well, it's going to have to look like this. It's going to have to go from like, well, I guess we don't need all that access, right? We can just maybe make it set up kind of like this. And that we have, you know, maybe -2. I like to go 1 unit beyond, and then maybe to 30 because the x-intercept's at 28 here. So let's make it axis from 2 to 30. And then the bottom of this axis is going to have to be like -60,000. And then the top of this axis is going to have to be, oh God, what would the top of it have to be? And scroll, 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 scroll. Come back to me, come back to me. Looks like it's going to have to be, oh, this local max is at like 20. Okay, so like 20. Oh, that's funny. Well, let's see what happens when I put that into Desmos. Okay, so you can actually change the viewing window in Desmos in case you haven't figured this one out. Um, Choose the little graph settings button here, and I'm going to say, um, x-axis, we're going to go from -2 to 20. Oh, look at that. And yeah, you've got that nice little shape there. But then I'm going to do um, my y-axis from -60,000. Wow. Um, all the way to 20. Whoa. And look at that. Look at that function right there. And I'll even scroll it back a little bit. That's wild, isn't it? And there's a picture of the function. Craziness. Okay. Well, so choosing a viewing window, um, a lot of times you have to start with the x-intercepts. And from that, you can then scroll down and kind of pull the screen back until you can get a range for where some of the local mids and local maxes are, um, to kind of give you a sense of what the graph is going to look like. And then even if you need to scroll from there, any of that's totally fine. And you can always update your settings, right? Okay. All right, next piece. What's the equation? So write a possible equation for a polynomial whose graph has the following horizontal intercepts. Oh, this is the reverse question. Up until now, I've given you the factors, and you've always just said, okay, the solutions are this. Now we're going to do it the other way. And now, given the solutions, you tell me the factors. So let's look at this first one. 4, 0. So it passes to the point 4, 0. That means that x equals 4. That's an x-intercept. And so what factor produces that? X minus 4. So x minus 4 is a simple polynomial that passes to that point. And I can add more factors if I want. No matter what, if I can add like an x plus 1 or an x minus 2, doesn't matter. As long as it has an x minus 4 term, it's going to pass through that point. But what if I want it to pass through 2 points? Well, then they're both have to be present, right? So not only does x minus 4 have to be present, but x minus 0 does too. Now wait, x minus 0 is just x, isn't it? X parentheses x minus 4. What if I want to throw a -2 in there? Now I've got x plus 2 times x minus 4. And so the x plus 2 is what would give you a solution of -2. And we can build polynomials in this way. If I want a graph that crosses through -4, 0, and 2, then it's going to have an x. It's going to have an x minus 2 term, and it's going to have an x plus 4 term. How about this one? Um, it's going to have um, a x minus 3. It's going to have an x plus 5. Oh, it's a fraction. Well, you could do x minus 1/2. Nothing wrong with that. Although, truth be told, we try to avoid fractions where we can. Um, so one way that we could potentially do this, although this works, um, one way to avoid the usage of the fraction here, because that's kind of weird to look at, is you could multiply this by 2, introduce a scale factor of 2 until you have x minus 3, x plus 5, and 2x minus 1. That also works as well. And that just has a scale factor of 2 associated with it, but it's still going to cross through all three of those points. And I can add a scale factor like that on any of the other ones. Doesn't matter. So it's easy. If you know the factors, you can write the solutions. If you know the solutions, you can write the factors. Okay. So that's the big connection. No matter what, no matter how many factors you have, no matter how many intercepts you have, that connection always exists. If you have a factor of x minus 3 and you have a solution of x equals positive 3, that road goes both ways. Always. Doesn't matter about scale factors. Sometimes those are there, but they just change the general shape. Um, but as long as whatever factors you have, we'll always cross the x-intercept at those points. Okay. So this kind of again goes to show you the possibilities that happens for that scale factor, right? So whether you have a scale factor of 1 or a scale factor of 2, all that's going to do is just change the pronouncement of the slope of each of those sections. Use a fraction if you want to make it a gentler curve. Use a higher number if you want a more steep curve. But it's still going to pass through the roots that it's supposed to. And that's it. Well, we got through three things all at once because they all have a big connection to it. Okay. I hope that enlightens you a little bit about fractions and factors and zeros and polynomials. And you guys have yourselves a lovely day. Maybe quiz soon. Go study. And keep working in that blue packet, will you? All right. Have yourselves a lovely evening, folks. Good night.